Okay, hello. Does anyone can hear me?
Mister Persson.
We'll come back in a few lifetimes.
Okay.
Give it.
Olivier, can you hear me?
No, I can't.
What a joke.
The sound is terrible.
The sound is terrible there here.
Yeah. I mean, it's better when you're talking, but otherwise, I mean, I don't know. What kind of mic do you have?
We are here for the moment. We're only using the my headset microphone. In fact, there is some issue with the sound diffusion in the room, so we need to manage some stuff. So we have a little GBL Bluetooth speaker. So, but we need to manage the feedback between my microphone and then when you will have to speak.
Okay.
Just to be very, very loving to the room for having it ready in case the sound system. We're working really hard on making it nice. Just be ready. Okay. This is a bit late today.
Ok. Et là, tu m'entends toujours bien?
Ouais.
C'est moi qui t'entends pas en fait.
Qu'est-ce que vous m'entendez pas?
Ouais, je t'entends. Ah, c'est un peu, c'est la bricole là.
Ouais. Où Christian il est là?
Ouais, Christian est là, bien sûr. Fatigué.
Ah bon? Vous avez fait quoi?
Ouais. Bon, attends, je vais prendre mon micro-casque là parce que c'est.
Oh putain, t'as une voix d'outre-tombe. Qu'est-ce que t'as foutu hier soir?
Bon, rien, mais bon, on se couche tard un peu tous les soirs, quoi.
Ouais. Faites un peu la fête.
Non, c'est pas vraiment la fête, mais on boit des coups, quoi.
Ouais, putain, t'as la voix un peu de Marie White quand même. Hein.
Un peu, ouais. Ce matin, c'est vrai que. Ah! Ah bon?
Ah,
Ah, mais
c'est
enregistré sur YouTube.
Oh putain.
Ok, on est enregistré sur YouTube, alors on va être discret maintenant.
Bonjour Olivier.
Monsieur était.
Ben oui, bonjour.
Toi, t'as une voix normale, toi.
Ben oui, c'est normal.
Oui, mais pas Renaud.
Ah, non. Je ne te dis pas. Je ne te dis pas.
Rien qu'en disant ça, tu me dis beaucoup. C'est pas ce qu'il a fait hier soir, Renaud, mais aujourd'hui, sa voix parle pour lui. Hein.
Ben, ça ne date pas seulement d'hier soir. Tous les soirs, il enchaîne. Tous les matins, il se réveille en disant, bon, je vais être raisonnable, mais les soirs, c'est un peu compliqué. Un peu compliqué. Et pareil, tu étais malade.
Ah ouais.
On n'était pas sûr de ta voix ce matin.
Bah si. Moi,
Tu
ça va
n'as
mieux
pas
que lui.
confirmé. On a envoyé des mails et des mails, mais comme d'habitude, tu n'as pas répondu. Donc, on se posait les questions.
Et je sais, Renaud a envoyé un message.
Eh ben voilà. Ben oui.
Qui me dit mot consent. Je ne disais rien parce que je n'avais rien à dire.
En passant, t'es en congé ou pas là? Tu seras en
Ah non.
congé ces jours-ci ou pas?
Non, pourquoi?
Ouais, non, il faut qu'on se voit. Il y a 2 gros bugs là que Seb a détectés.
Oui, je sais, dans Croco, ouais.
Non, pas dans Croco, dans Nemo.
Non, ah bon?
Ouais.
J'avais
Il y a,
l'impression que c'était.
bon,
Ouais,
en
mais j'ai
fait,
vu, c'est dans PKZ FLX, non.
non, PKZRM.
Ah, PKZ, ouais. Bon, il faut que je
Ouais,
regarde. Je
ouais,
les ai
ouais.
vus en passé, mais en fait, j'avais l'impression que c'était du Croco parce que c'était des
Ouais.
indigènes. C'était sur, je crois que c'était le bug avec K.
Non, 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 non. Il y a des boucles qui font du JK-1, mais ça commence de 1 à JK. Bon, en fait, je n'ai pas compris les paramètres à l'intérieur. C'est juste pour ça aussi. Il y a 2 paramètres là que je vois pas. Difficile à corriger si on ne comprend pas ce que ça fait. Dans PKZRM, tu vois, regarde le mai de 7.
Je sais, il y a un truc sur le proxy bactérien au début, là.
Ouais, exactement. Et après, il y a un autre.
Ça, je vois pas pourquoi ça pose un bug. Ça peut poser un bug, en fait, si tes boucles sont à l'envers. Donc, si elles
Non,
sont
parce que
pas.
non, parce que tu fais un if-else. Et donc, dans le if, là, effectivement, donc dans le else, c'est dans le else que tu utilises un tableau qui n'a pas été initialisé, en fait.
Si, mais
Tu
s'il
verras.
est initialisé. Oui, alors il n'est pas initialisé, mais en fait, il est rempli en fonction des premiers niveaux de la colonne d'eau. Or, comme
D'accord.
dans Nemo, tu commences par les premiers niveaux.
Ouais, mais ça marche pas. Ah oui, oui, mais bon, mais le compilateur n'aime pas. Parce qu'effectivement, il
Oui, parce
considère que.
qu'effectivement, le tableau n'est pas initialisé. Oui.
Voilà. Bon, jusque-là, ça va. Mais celui d'après, bon, tu verras, on en parlera.
Je regarderai,
Celui
ouais, mais
d'après, j'ai pas. Ouais.
en fait, j'étais hyper surpris parce que je croyais que c'était un bug croco et
Non,
je
non,
me
non,
dis
c'est un bug Nemo. C'est un bug
Step
Nemo.
travaille sur des bugs croco.
Ouais, non, c'est parce que Christophe allait le voir pour lui demander de compiler avec GFortran pour tester, voilà, et il a compilé avec GFortran des bugs, et bon, ça lui a sorti des trucs forcément, voilà, que eFort ne sortait pas, quoi, dans des bugs.
Ouais, ok.
Bon, c'est pas qu'on regarde ça. Ok. T'es à la maison, là, ou... Non, t'es au bureau.
Ouais, je suis pas tout ça.
Ouais, ok.
Ah, j'ai fait du télétravail quasi toute la semaine dernière, c'est bon, j'en ai marre.
Ouais. Donc, t'as une réunion à 10h30, comité de direction.
Comment?
T'as une réunion à 10h30, non? C'est le comité de direction, ou... c'est ça, non?
Ouais, non, c'est un autre truc où je m'étais engagé, mais comme la date, le jour du talk là, pour l'école, c'était pas clair. En fait,
Ah,
c'était lundi ou mardi ou mercredi. Bah, j'ai pris des trucs quand même. Au début, même, c'était mardi, je crois.
non, c'est lundi.
Ah bon?
Ouais, t'as raison, c'était mardi, c'est vrai. Ah, c'était mardi. Je
Voilà,
savais pas trop, c'était mardi.
ouais, et donc j'avais pris des trucs le lundi et en fait, enfin, la semaine dernière ou il y a 2 semaines, j'ai vu que
Ouais.
c'était lundi. Ouais. Mais
T'as prévu combien de temps alors pour le talk? 45 minutes? 1 heure?
ouais, peut-être 50 minutes, je dirais.
Ouais, 10 minutes de questions quand même. Ouais, bon, il y aura des questions.
Pas s'il y aura des questions.
Ouais, ok.
Vous avez fait du bateau hier, c'est ça? Il est parti.
Tu peux déborder de combien de temps, toi, Olivier?
Comment?
Tu as une limite ou pas en termes de. À 10h30, tu attaques ta réunion directement? Il faut qu'il soit à l'heure où tu as une
Elle
petite
commence à
marge.
10h en fait, ma réunion,
Ah ouais, ok, d'accord.
mais c'est pas grave. J'ai dit que je serais en retard d'une demi-heure, donc 10h30, 10h35, 10h35 comme tu as dit hier.
Ok. On attend encore 1 ou 2 minutes et puis j'introduirai la session et après je te passerai la main.
Ah, oui. Je vois pas du tout la salle, là. J'ai aucune idée de...
Ouais, je peux te mettre mon micro. Hein? Bah, peut-être pas tarder, ouais. On va attendre une petite minute.
Tu peux pas me montrer la salle?
Attends.
Google.
Alors. Here is the room, Olivier.
Ok. Hello.
You are not alone. So, Jenny, what option?
So this should work, but the problem is when you talk.
Yes, there is feedback.
So I have to turn it off.
Okay, you turn it off and then you turn it on when
Can
Olivier.
you just test that it does feedback?
Yes.
Unmute. And I'm a little bit worried it's not paired anymore. JBL flip, it should be fine. So can you talk?
Okay, so good morning, everyone.
Yes, there is an echo.
There is an echo, yes. It's not really.
When you talk,
yeah.
but when
Olivier.
if you mute
Okay.
and Olivier talks,
But there is an echo. There is still, yes, there is a feedback.
it's not coming through here though.
Okay, there is feedback now. Yes, but in fact, even if I speak louder, there is some kind of echo and as well feedback. And Olivier has always an echo.
But when Renaud is talking,
Yes.
Coming through here.
so because you are talking, no, there is a feedback. Wow. Oh, yes, that's when I'm talking. in
Try to do
fact.
that.
Oh, no.
Okay, Olivier, tu m'entends?
Oui,
Can you hear me? Yes.
yes.
Any feedback on something on your side?
No. When you're talking with your, I don't know what you are using, but with your laptop, I mean, it seems to be okay.
Okay.
That's when Jenny is
The laptop
talking.
is okay, but it's when we switch to the JBL speaker.
It should be on though. The JBL is on.
Is on?
I'm not hearing Olivier through the JBL.
No, that
So
I think that's when Jenny's mic is on. But
Yes.
maybe I just need to pair them again.
Right, front, left.
Okay.
Hello?
Okay, Olivier.
Yes.
I switch. I mute my microphone and we see. Olivier, can you speak, please?
Yes, 1, 2, 3, 4 seems to work. No feedback.
We can't hear us here in the room, so.
why we don't
The output is on the GBL. Maybe we can. Hello.
It's fine.
Okay, Olivier, can you speak, please?
Yes, 1, 2, 3, 4, 5.
Yes, you come perfectly. Until 5.
Until 5 at least, yes.
I don't know why you don't have a sound now.
Okay.
What happens?
I think that we need to use headset for anyone in the room because we don't have much time. Yes. We don't have much time. Yes.
Okay. Okay.
We don't have much time. Yes.
Can you
Olivier, can you speak? Hello?
Oui, yes.
Can you speak now, please?
Yes, I can speak. Is everything going on? All right.
Okay. Can you start, please? Thank you.
Okay.
Maybe.
Wait, sorry, Renaud first has to
Okay, I will do a brief. Welcome to this training session on the marine biochemistry. So this morning there will be
I can't hear anything from the room.
Okay, I've unmuted.
okay. No, no.
Switch on your mic, Renaud. I think it will work with your mic.
No, it doesn't try.
Okay. Can you, hello everybody, and Renaud, can you switch off? Thank you, Jimmy. Can you switch off your sharing your screen? Yes, great. So that I can share mine. Okay. Can you see my screen? Yes, great. Okay. Here it is. Oh. Okay, so can you see my screen well? Okay, thank you. So, okay, this session will be mostly about presenting the basic principle of marine ecosystem modeling. And then in a second step, very briefly, I will present the main structure of PSCS and how it is structured. Okay. So when we talk about marine biogeochemistry, we talk about a lot of processes. So here on this slide, you have a simplified sketch of the different biogeochemical processes or processes affecting biogeochemical cycles. So I say simplified sketch, but you have already, even in this simplified sketch, you have a lot of processes going on. So I won't detail all the processes, and generally, not all of these processes are modeled in biogeochemical modeling, in biogeochemical models. And so these processes at play, they are all coupled and they are of different nature, of different kinds. So you have biological processes like photosynthesis, respiration, trophic interactions, which may even be classified as ecological processes. You have chemical processes like iron chemistry, carbonate chemistry, and you have physical processes. So physical processes, there are two kinds. So you have the ocean dynamics and its impact on marine biogeochemistry. And you have also other types of physical processes like sinking particles, aggregation, coagulation, all that kind of processes. You also have the active swimming by big animals. So to understand and to improve our knowledge in what's going on in the ocean, there are three different means to do that. So the first mean is to do direct observations in the ocean, at the surface or in the water column, and you have a very, very wide range of tools to observe the ocean, like cruises, traditional cruises, buoys, gliders, satellite sensors, etc., etc. The second kind of observation or tools to understand the processes going on in the ocean are experiments in the lab or in controlled environment, not necessarily only in the lab. So you have, of course, experiment in the lab, like in a microcosm, but you may also have experiment in the field with mesocosm, so large tanks or large pools of water which are supposed to better mimic the natural environment. And the third means, which is what we will talk about today, is modeling. And so when we talk about modeling, we talk about very, very different types of model. And I will briefly, or not so briefly, but not in too much detail, present the different types of modeling that are used currently. So modeling, probably you all know that, but the question is, why do we model? So why is it useful to model the ocean? So there are different reasons, and so it really depends on the scientific questions you would like to address. So the first typical way or reason why using model is to do hypothesis testing. So if we add, remove, or change something in the system, what happens? And so it's way much easier to do that in a model than to do that in the real world. The second reason is to do to develop a quantitative dynamical framework. And so for instance, to test some data sets or some parameter estimates with a model and to see if that makes sense with respect to what is observed. Assessing some unknown rates and parameters, so pretty much you have some observation and you can use a model to try to estimate some rates, fluxes, properties that would be otherwise very difficult to, or sometimes even impossible to estimate in the field or in the lab even. So the fourth reason is to do some prediction forecasting. And so like doing climate change forecasting with ESM, Earth System Models, that's typically one common use of biogeochemical models. And it can be used also to help designing an observing system or campaign, like testing the best, designing the best sampling strategy. So this is a brief of this is an overview of the presentation. So the first part will be on how to construct a model. So the basic principle behind a model. Then I will make a short historical perspective on modeling. In a third step, I will detail on the different framework to represent the physiology of the organism, then how to model functional biodiversity, some final words, and then I will briefly talk of Pisces. So the basic principle behind all biogeochemical model is the mass conservation, or the equation of mass conservation. And so a tracer in the ocean or an entity in the ocean is conserved. And so its time evolution is the sum of physical processes like advection, diffusion, and some biogeochemical sources and things. And so the only thing we'll talk of today is biogeochemical sources and things. That's what is doing a biogeochemical model, to model the biogeochemical sources and things. So the first maybe consequence of that equation is that if we want to do some biogeochemical, or when modeling biogeochemistry, it requires an ocean circulation model. We need some physical information. It can be very simple, but generally we always need an ocean circulation model. It means also that any biases in the simulated ocean dynamics produce a bias in marine biogeochemical and ecosystem models. So if your circulation is not well represented, no chance to get a good state with your biogeochemical model. And it means also that all the challenges related to dynamical modeling are pertinent for ocean biogeochemical modeling, like modeling mesoscale, sub-mesoscale, mixing, overflows, boundary layers, and so on. And so coming from that, there is a first challenge, which is the computing cost. And so there is some kind of a tension between better modeling the ocean circulation, which means generally to have better parameterization or to increase the spatial resolution. And on the other hand, better modeling the ecosystem means that you have to increase the number of processes and prognostic variables. And so you see that there is a tension between increasing the resolution or making the ocean circulation model more complex and making the biogeochemical model more complex. And just to illustrate that with the resolution, here are three different configurations of a global ocean modeling platform, NEMO, with the ORCA global configuration. And so ORCA 2 is 2 degrees resolution, ORCA 05 is 0.5 half a degree resolution, and ORCA 025 is a quarter degree resolution. And so if you go from 2 to 5 to 05, it increases the computing cost by 32. And if you go from 05 to a quarter, it's by a factor of 8. So it means that if you want to model the global ocean with a quarter degree resolution, you have to increase the cost by more than 200. So then we switch to an historical perspective. And so when biogeochemical modeling was introduced and where we are right now. And so it's a long story, not so long, but it's not a very recent story. So the pioneering studies date back to the middle of the 20th century with the first marine biogeochemical or ecosystem model that was introduced just before the 40s by Fleming. And so it was a very, very simple model where there was a very simple equation modeling phytoplankton biomass. And you see that the time evolution of phytoplankton biomass is the difference between the growth rate and a mortality rate. And the objective was to simulate a diatom bloom in the channel. And you see here the observation with the dashed line and the model with the straight line. And you see that the model was able to capture the first order pattern, so it was able to simulate a bloom. The first NPZ model, NPZ means nutrient phytoplankton zooplankton, was introduced quite almost 40 years later, 35 years later, and it was the first model that was fully represented a closed biogeochemical system. So you have, it was the first NPZ model, and all models now rely on this formalism, the NPZ formalism. The pioneering study, which is at the basis of all modern biogeochemical model, and where all the important ingredients and formalism, theoretical formalism were introduced, is a study by Fasham et al. In 1990. And so it was an NPZD model. D means detritus, and you can see the structure of this model. And so all models currently used, almost all models currently used, are based, have a flavor or are based on this structure. And so this model was used in a 0D or quasi-0D framework at different stations, mostly in the North Pacific and North Atlantic Ocean. And you see for some variables, for some observed variables, nitrate and phytoplankton biomass, you see the performance of the model. So basically in 1990 or during the 70s and the 80s, most all models were used in a 0D or quasi-0D framework. That's really at the beginning of the 90s that the first biogeochemical model were used in specially resolved biogeochemical models. So it's only 30 years ago that that really specially structured biogeochemical models were designed. And so the first model at the global scale was the AMOC model developed by Ernst Mayr-Reimer. You see a photo of this, a picture of this guy here. And so it was a very, very simple biogeochemical model, which is even more a geochemical model. So a single equation for the whole biology. So it means that a single equation to represent this type of processes. And so in fact, export production was made a function or was computed as a function of temperature, light, and phosphate. And so that's the simplest models that are used in the global or in global ocean models. And some models are still currently based on this framework. So this type of model were extremely cheap, but it was necessary at that time considering the computer power that was available. It also meant that even at that time, long-term simulations were feasible. So to address paleo, future, steady state studies, they were doing a decent job at reproducing the large-scale patterns. And you see here a distribution of phosphate in the Pacific Ocean along 180 west, and what the model is predicting. And you see that it is able to capture the first order patterns. You see here, for instance, that you have a large accumulation or unrealistic accumulation of phosphate, but it's not due to the biogeochemical model. It's due to the very coarse resolution, about 4 degrees of the ocean dynamical model. So it's a way also to illustrate that any bias in the ocean circulation implies biases in ocean biogeochemical model. And so current methods perform better, but they do not perform a lot better than this type of model. And most of the improvements with more complex biogeochemical model comes from a better representation of ocean dynamics. And that's what I mean here. It's for large-scale annual mean patterns. Then in the 90s, so in the mid-90s, the first NPZD model based on Fasham, which I call Fasham-like models, were introduced in specially resolved ocean system. And so in 1993, there was a study of the North Atlantic, and in 1993, there was a study at the global scale by the same group in Germany, so Katharina Six and Ernst Mayr-Reimer. And so they were quite simple NPZD model with 4 or 5 compartments. And so that's a brief example or a rapid example of how the model, this type of model was performing at that time. And so that's from Six and Mayr-Reimer at the global scale. And you see some satellite observation of annual mean surface chlorophyll, and you see what the model was predicting. And without taking a lot of time to describe the plots, you see that from at first sight, it performs quite well, or at least the main patterns are reproduced by those models. And then, since that time, models have become more and more complex. And so from very simple NPZD model with 4, 5, 6 compartments, now we are using more complex model with many more prognostic variables. So for instance, more nutrients, more phytoplankton groups, more zooplankton groups, and so on. So some basic, some important statement at that stage, more complex does not necessarily imply more realistic. So a more complex model does not necessarily perform much better than a simple NPZD model. And also a problem with more complex biogeochemical model is the fact that you have a huge set of often badly constrained parameters. And so we come to the second challenge, which is tuning the model. So when you have a biogeochemical model, you have a huge set of badly constrained parameters, and so you need to tune those parameters to be able to match to a certain extent the observation. And so you have several ways to do that. The most common way is to do hand tuning. So basically, you have a list of parameters, you change one parameter, you run the model, you evaluate the results, and you have some kind of an expert judgment saying, okay, the model performs better, no, it's not performing better, and so on. And so you do that. Most of the time, you have to do that 10, 20, 100 times, even sometimes more than that. And so it's often a pain. But we learn a lot from the model dynamics. So some kind of what I call an intuitive knowledge of the model behavior. You have some more advanced techniques like data simulation approaches, like using inverse or linear adjunct models. But you have numerous difficulties. And for instance, one difficulty is that, as I said, you need an ocean circulation model. And so when you constrain the parameter, you may overcompensate for biases in ocean dynamics. And with a data simulation approach, you don't necessarily know why you tune the model and if you do it for the right reason. This challenge is often hidden, and here is a brief overview of a study that was published by Shimoda and Arunditis in 2016, showing how often you can see a quantification of the goodness of fit of the model, so quantification of the skill of the model at reproducing the observation. And so in about half of the observations, there is no sensitivity analysis. So there is a single set of parameters, and there is no sensitivity analysis to infer how sensitive the results are to the assumption on the parameters. In about a third of the study, there is no validation presented. And in most studies, there is only a partial validation of the simulations. And the goodness of fit is most of the time not properly quantified. And so that's something that is you have to be aware of. So it's very, very important to quantify in a proper way your state, so your simulations. So the third part, we come to the third part of the study, which is representing the physiology of the organisms. So there are different ways to model the living compartments in a model, and I will present here three different ways, the three main different ways to represent the physiology of the organisms. So the most simple way and the oldest way is to represent phytoplankton, and here I will mostly talk of phytoplankton physiology. The simplest way is based on the monoformalism or red field formalism. And so in this formalism, phytoplankton growth, so you see that on this equation, phytoplankton growth is a function of the external availability in nutrients. So you have a maximum growth rate and what we call a Michaelis function of the external nutrients. And so it means that to represent the phytoplankton, we need only one tracer, one pool. We need, of course, also a pool for the nutrients, but to model phytoplankton, only one pool. One consequence is that if there is no nutrient in the medium, that instantaneously phytoplankton growth ceases, stops. So this formalism was introduced in the 40s, and that's basically, well, okay, in the 40s. Then you have a more advanced way to model phytoplankton physiology, which is the quota or the droop formalism. So in that case, instead of having only one variable, you first have some internal stores in or content in the different nutrients. So you can have an internal pool of carbon, of phosphate, of nitrate, and this pool is a function of the external availability in nutrients, so the uptake of these nutrients, and a function of growth rate, so what we call dilution by growth. And growth of phytoplankton is a function of this internal pool. So here is an example of that equation, of a possible equation. You have different types or different ways to make phytoplankton growth or different types of parameterization. This is one of them, the most typical one. And so in this formalism, it's more complex. So you have more, you need to model more pools. So at least two, one for the biomass and one for the abundance, and one for at least one internal pool. And so you need also to represent generally one pool by nutrient you will have in your model. And so if you have phosphate, nitrate, you need to have the carbon quota, the phosphate quota, and the nitrate quota. Most biogeochemical, so an important characteristics of this quota model is the fact that in this case, when nutrient reaches zero in the system, then phytoplankton growth doesn't stop instantaneously. So it continues to grow until the quota reaches the minimum quota. So the main difference with the mono approach is that it's not driven instantaneously by the external availability in nutrient. And this is more realistic. And so most biogeochemical model or ecosystem models belong to one or the other, to one or the other of these classes. But you have more advanced way to model cell physiology. So in the 70s, so quite a long time ago, so 40 years ago, Schutter and Schuller introduced what is called macromolecular models. So it's a little bit like the quota model, but it's an evolution of the quota model. So instead of representing a raw store or a raw content in carbon, phosphate, nitrate, and so on, in fact, we represent either some organoids in the cell or some pools, like we can represent the photosystem, the nucleus, the photosystem, the nucleus, but we can also represent the amino acids, the proteins, etc., etc. And so in general, these models are represent in a more detailed way the cell physiology, but they need many more tracers. So generally about 10 tracers. So that's a raw number. So generally it's 5, 6, 7, but it's more than in the group model. It's more because you represent more pools. And then during the year 2000, with the emergence of the omics techniques, much more complex models have been developed. So of course, I won't comment the picture here, which are based on full metabolic reconstruction or flux balance analysis. And so instead of representing aggregated variables with a coarse resolution of the physiology, this type of model represents all the metabolic, or try to represent all the metabolic reactions. So it's very, very expensive, but it's very promising because you represent all the reaction and you can represent the cost of the different reaction and the cost of investing in one reaction or one metabolic pathway instead of another one. And it's also useful to identify new metabolic pathways. And so we switch now to another important aspect of biogeochemical modeling or ecosystem modeling, which is modeling functional biodiversity. And so you model the diversity of phytoplankton. So you model the physiology of phytoplankton, but there is, in fact, different groups have different physiology or have different rates, metabolic rates. And so representing the physiology of only one cell can lead to very strong approximation or errors. And so there is an underway effort to be able to model the functional diversity. Functional means that instead of modeling the taxonomic diversity, we model the diversity in terms of functions, biogeochemical or ecological functions. So why is it important to model functional biodiversity? So I say that, in fact, the physiology of the cell or some traits or some aspects of the cell's species depend on the diversity. And so, well, as I said, when we talk about biodiversity, we talk about functional biodiversity. And so here, there is an illustration of two aspects where biodiversity may be important. So here on the left, you have the optimal N-to-P ratio of the cell. And you see that the N-to-P ratio is quite variable depending on the different groups. So for instance, cyanobacteria have a high N-to-P ratio, and diatoms or dinoflagellates have quite a low N-to-P ratio. And you see also here that biodiversity, productivity of the system depends on the diversity. And so you see that the productivity is more variable when the diversity is low. No problem. Okay, and so there are different ways to model the biodiversity. So the first and probably most common way to model biodiversity is the plankton functional types models. And so plankton functional types are basically types of phytoplankton that do have a specific biogeochemical ecosystem function. They should, PFT could be allocated, or they could be differentiated. So they could be allocated a distant set of physiological, environmental, food characteristics. And of course, a PFT should have some importance in a region of the ocean. And here you see an example of an idealized plankton functional type model published by Leclerc et al., who introduced that concept of plankton functional types model. So you see, for instance, that you have in this sketch 6 different phytoplankton groups, like, for instance, nitrogen fixers, like trichodesmium. So this PFT is defined as cyanobacteria that are able to fix nitrogen. You have coccolithophorids that do build a calcium carbonate frusture. You have diatoms that do use silicon and that are making silicon frusture, and so on. But there are some drawbacks or some difficulties associated with PFT models. So first, the first problem or the first difficulty is that numerous species are lumped into a limited number of boxes. So here you have 6 boxes, so that may seem complicated, but of course, it's a very, very, very naive and simplistic way to model the full diversity in the ocean. And so within diatoms, you have hundreds of different diatom species. You have to make a choice of how many boxes should be set and how to set a single set of parameters for each box. Third difficulty is that you assign a fixed a priori defined structure of the model. So it means that the structure of the model is fixed. And so if you apply that model to another region or to another environment, then it may not be adapted anymore. And tuning becomes quickly a pain because instead of having, let's say, 20 to 30 parameters, you may end up with having hundreds of parameters. So the more groups you have, the more parameters you have, and the more complex it is to tune the model. The second approach is trait-based model. So what is it? So in that case, instead of what we have in the PFT, we don't model species, we don't model groups. So what we do model is that we do model functions and that we call traits. So organisms are identified by a few taxa transcending properties, and so the key traits and the trade-offs between them. And the structure and function of ecological communities emerge from properties of the individual organism. So you don't set a priori the composition of the system, it emerges as a dot or a state in this space of different states. And so here it is an example of a trait-based framework where you have three traits which are photoautotrophy, heterotrophy, and nutrient acquisition. And so you have a competition between these traits, meaning that if you invest a lot in nutrient uptake, you will invest less in phototrophy or phagotrophy. And so the model is predicting a point there or a state in this space of states. So it seems attractive, but you have some difficulties. The first one is what traits should we represent? And so here there are three traits, but there could be many more or other traits as well, like size, for instance. Quantifying the trade-offs is very often challenging, and that's where metabolic reconstructions that I introduced earlier on can be useful, or at least it seems to be promising. All traits are most of the time accessible everywhere all the time, and so there is a question of how to model evolution. So it means that every trait can be, every point or state in this space trait can be reached, and so there is a question of evolution. And it can be very, very, very expensive because adding a trait to the system means adding a dimension. And so instead of having 3 dimensions, spatial dimension, you may have 4, 5, 6, 7 dimensions. And so the cost is increasing a lot by when adding traits, a supplementary trait in the system. A very well-known trait, which was not represented in this theoretical framework that I mentioned, is size. So size is considered as a master trait. Master trait because a lot of other traits depend on size. So for instance, many metabolic rates show some dependency to size. That's what is called allometry. And you have an example here for metabolic rate as a function of mass, which is another way, proxy of size. And you see some kind of relationship from cells, protists, to big animals like elephants or humanity, men. Okay, let's call that men. There are many processes, fluxes that are impacted by size, like the sinking of particles. Larger particles sink generally faster than smaller particles. Feeding strategy. So feeding strategy is impacted a lot by size. Motility, vertical migrations. Trophic interactions are influenced by size, like who is eating whom. And biomass distribution is often shows some kind of regularity with size. And you have here an example of the abundance as a function of body size, and you see some kind of organization with size. And so smaller organisms are much less abundant than larger organisms. Most current models are in fact mix both approaches. So it's not, most models are not pure PFT models or pure trait-based model. Generally, that's a mixture of both approaches. And here it's an example of perhaps one of the most complex model that is existing in the literature, which is a Darwin model developed at MIT. And you see here the structure of this ecosystem model. And you see that you have 5 groups. So it means that 5 PFTs. So it's partly based on the PFT approach, but you also have some traits, mainly the size and the thermal norm. So the optimal temperature at which the species are adapted. And so size and the thermal norms are traits and groups are PFTs. And so it's really a perfect mixture of both approaches. And the most recent type of models that have been developed or proposed in the literature are gene-centric models. And so the objective of that type of model is to bring together metagenomic data and biogeochemical model. And it's very, very challenging for many different reasons. And one reason is that they differ in the considered currency. So omics data refer to genomes, proteins, metabolites, and are not all the time quantitative, and biogeochemical models refer to concentrations, biomass, and biogeochemical functions. The first approach, so the first gene-centric approach has been proposed by Reed et al. In 2014. And so organisms are grouped according to their functional genes and metabolisms, not as a function of traits or taxonomic or biogeochemical functions, but as a function of some genes. And a problem is that as most organisms in the sea are uncultured, simulating their genes is impossible. And an alternative is to randomly allocate genes from a known pool to construct a set of organisms. So instead of representing some real organisms, some real genomes, we in this approach, some artificial synthetic genomes are constructed because we don't know all of the genomes that are existing in the system. So we just do like the nature and we simulate really, we create artificial organisms. And the environment selects the one that could survive in the system by generally Darwinian pressure. Here is an example of a gene-centric modeling study, so Cole et al. 2017 in the Atlantic, in the tropical Atlantic Ocean. And so here, in this type of, so I won't detail that too much, but in this type of approach, so instead of simulating biomass or etc., we are also only simulating biomass. We are also able to simulate different types of genes, genes associated here to nitrogen physiology. And so we are able to simulate that, and we are able to use data, genomic data, to evaluate the performance of the model. And we are also able to reconstruct metagenomes, for instance, here in the Amazon River plume. So it's a metagenome, and it's an artificial metagenome. So it means that the model selects the type of genomes that could survive, that are selected by Darwinian pressure in the system. It's not an ingredient that was given by the model. It's really something that is emerging from the model. So these approaches that link together omics and biogeochemical ecosystem are still in their infancy, but they are rapidly growing, but they are very, very difficult because they are also very, very expensive. So some final words on this first part is that what I presented here is a brief and subjective overview of biogeochemical ecosystem modeling. Many aspects have been omitted, like eutrophic levels, evolution, niche modeling, micronutrients like iron, etc., zinc, and so on, diagenetic and benthic processes. Many challenges have not been mentioned, and I probably do not know all of them. One of these not clearly stated challenges is to bring together an increasing number of very diverse expertise. So like mathematics, computer science, physics, physiology, biogeochemistry, ecology, omics, and so on. And of course, something you have to keep in mind is that whatever the model is, even if it is very complex and very detailed, it's not the real world. And so they are always imperfect. and necessarily show some level of deficiency. And so you also have to keep that in mind when using a model. So we switch to the second part of the presentation, which will be much shorter. And so to give some basic information on PSCAS. And so PSCAS is a mixed PFT and PZD type model, but it's way more simpler than Darwin, the model introduced in the first part of my presentation a few slides ago. And so this is a basic description, this is a description of PSCAS. So in PSCAS, you have 5 different nutrients. So you have nitrate, ammonium, phosphate, silicon, and 1 micronutrient, which is iron. You have 2 phytoplankton groups, or explicit phytoplankton groups, which are nanophytoplankton and diatoms. And we model different pools for each phytoplankton group. And you have 2 implicit pools. Implicit meaning that they are not fully prognostic variables. They are diagnosed from environmental conditions and phytoplankton concentrations. And those 2 implicit pools are coccolithophorids, so calcite producers, and nitrogen fixers. And you have 2 zooplankton pools separated by their size, so micro and mesozooplankton. And you have a bunch of different organic, dead inorganic materials. So you have DOM and 2 size classes of particles. So this model has 25 tracers. So it's quite huge in terms of structure, but much less than Darwin, which has 70 tracers. Something also important is that it's a mono-based approach, or it's a mixed mono-quota-based approach. So it's a mono model for nitrate, phosphate, and carbon, and it's a quota model for iron. And so there is a second version of PSCAS, which is embedded in the same code, which is a quota PSCAS model. So the quota PSCAS model differs mainly from the standard version of PSCAS by the fact that it's based on the quota approach. So it means that for phytoplankton, we model the internal stores in carbon, nitrate, or nitrogen, phosphate, and also iron, chlorophyll, and silicon. And the second difference is that instead of having 2 explicit phytoplankton groups, we here have 3 phytoplankton groups. So in addition to nano and diatoms, we have phytoplankton. And we model phytoplankton because of something I said for biodiversity, because the N to P ratio of phytoplankton, and more specifically of cyanobacteria, is very different from the 2 other groups, which makes it important to distinguish, especially when we explicitly model the difference between nitrogen and phosphate physiology. So you will see that later, but a few words on the code structure. So this is the main structure, or the main directory, the main routines of PSCAS. So PSCAS is coded in Fortran, and you have some master routines. And so the main master, you have some routines to initialize the model, and you have some routines that call PSCAS. And so the routine that is calling PSCAS is TRC SMS _ PSCAS, and it's calling 2 different modules, 2 different types of module. So P4Z, which is the marine biogeochemical model. So this is PSCAS, I would say, by itself. And there is a SED directory, which is a diagenetic process module, a process model. And so in P4Z, that's where you have PSCAS by itself, so the SMS the routines that compute the biogeochemical sources and sinks. And so I won't detail all the routines, but something you see is that all the routines referring to PSCAS, to the SMS, start with P4Z or P5Z. P4Z is for the standard PSCAS model and the quota PSCAS model, and P5Z are modules that are specific to the quota version of the model. And something you have to remember is that the routines or the code is structured by processes. So it means that a module is referring to one or a set of processes. For instance, if you look at P4Z micro, it means that this routine is computing the sources and sinks of microzooplankton. P4Z or P5Z prod are computing the growth rate of phytoplankton groups, and so on. So it's not a single big routine in which, or big module in which you have everything. The choice has been made to split the code in many different subroutines to make it clear. So some statements about the difference between PSCAS standard versus PSCAS quota. So most of the optional features you have in PSCAS, or most of the processes you have in the standard PSCAS experiment, do exist in the PSCAS quota version of the code. The sediment module cannot be activated with PSCAS quota. So if you use PSCAS quota, you can't use a diagenetic module, because in the sediment module, you don't have a variable stoichiometry of the organic matter. PSCAS quota is significantly more expensive than PSCAS because it has more tracers. So in PSCAS quota, you have 40 tracers. In PSCAS standard, you have 25 tracers. And many parameterization choices are common to both versions. So I will also briefly speak of the sediment model, just to mention that it does exist and it can be very, it tends to be, or it's very useful when you do coastal modeling, because sediment can play or do play an important role in coastal areas. So in the default configuration, exchanges with the sediments are modeled based on a very simple meta model proposed by Middelburg in '96. And so it means that fluxes with the sediments are modeled as a function of the biogeochemical properties, some properties of the water column. So like the nitrate concentration at the bottom of the water column, oxygen at the bottom of the water column, the depth, etc., etc. So it means that we don't have in the standard version of PSCAS, you don't have an explicit diagenetic model. You have a toy model, I would call that, of the sediment. A full prognostic diagenetic model is embedded in PSCAS and can be activated by setting a tag, by setting a Boolean to true in the name list. And this sediment model can be used in a standalone mode, so it means without PSCAS, but in that case, the code needs to be recompiled. And when running with PSCAS, there could be two ways. There can be two ways to model to run the sediment model in a one way. So it means that the sediment model is receiving information from PSCAS, but PSCAS, the water column, is not getting any information from the sediment model. So it means that in the water column, it is using the meta model, but the diagenetic module is activated, and you have the two ways coupling, which means that they fully interact. This is a description of the diagenetic module of PSCAS. So I won't detail that too much, but just to say that it's a quite complex or complete diagenetic module, but not fully complete. So it may not be suitable for some specific and very productive and very anoxic environment, but we model different types of redox reactions. And we model, in fact, the oxic pathways for organic matter remineralization. We model denitrification, iron reduction, and sulfate reduction. So it should be suitable for most coastal environment, but not necessarily all of them. And I think I'm done. So thank you for your attention. I was a little bit too long, but that's okay.
I'm not sure who can hear the applause, but
Olivier?
Yes?
Okay, we'll just try to think. Okay, we switch off the speaker there. So, does anyone here in the room have any question on the presentation? Yes, Precious.
Can you use cases for the concept and standard cases? Like what are the different cases?
Different
that
use
find
cases?
you
You mean when should we use one version
Yeah.
or user? So, okay, Olivier, the question by Precious was, when should we use the quota version relative to the standard version? Meaning, in which cases we should use a version or another, which is not an easy question, in fact.
No, that's
wait.
hello,
we need
Precious.
to-
And so that's not a very easy answer. So I would say in systems where you have a huge imbalance between the different nutrients, for instance, and it means that in coastal areas where you have, for instance, river input, or you have a huge, where, for instance, you have large differences between nitrate and phosphate, nitrate availability and phosphate availability. Generally, you will have to use a quota model. Also, in systems that are very variable, all systems are very variable. But in systems where you have strong pulses of nutrients, like for instance in coastal operating systems where you have relaxation of the winds and strengthening of the winds, and so you have on a time scale of a few days strong pulses of nutrients. Generally, it's a good idea to use a quota model. For the reasons I said, because in a mono model, because there is no stores, there are no stores, no storage of nutrients. The model will, as soon as there is no nutrients, the model will stop simulating phytoplankton growth. But there is also another problem, which is as soon as there will be back nutrients in the red field or the standard version of Pisces, phytoplankton will grow straight away, really straight away, whereas it's not the case in the real world, and it's not what is simulated by the quota model. So that's where I would say some illustration of when a quota model would be more appropriate. But there is also something to take into account or to consider, which is the computing cost. And so, of course, because the quota model is more expensive than, or way more expensive, much more expensive than the standard version of the model, sometimes you don't have the choice and you have to run the standard version of the model. And so that's, and also especially if you have to make a compromise between resolution, the resolution at which you want to model the system, and the complexity, then it may be a good idea, or it may be suitable to use the standard version of the model. So there is no single simple rule. It's more, I would say, it really depends on the situation, on the system you're modeling, and also the means you have to model the system.
Okay, thank you. Any other question? Even for people who are online? Yes, another question from Precious.
So if you are running at the global scale,
Yes.
And so you can run maybe at a low resolution. And so I'm trying to figure out that if you run at lower resolution and use the standard and use Kotlin versus running at high resolution with the standards model, in terms of the nominal features of BTC, is there somewhat of a guide about that?
Okay. Okay. So the question is there any advantage, I would say, to use the quota version in a global configuration at low resolution rather than a standard version at high resolution? If I can resume your question.
In fact, I know I have the answer because I did both. So I would say again, it really depends on what you're interested in. So, but it really depends. So there is no single answer. But I would say if you're interested in chlorophyll, for instance, or matching reproducing chlorophyll distribution, or you want to investigate chlorophyll variability, or etc., etc. Or if you're interested in RCCO2 fluxes, no. Frankly speaking, having a quota model is not very useful. I mean, you have some differences, but objectively, I mean, in terms of chlorophyll, a quota model is not performing, for instance, much better than a standard model. Same for PCO2 distribution or RCCO2 fluxes. So I would say it really, and also for the main nitrate, I mean, for instance, the large-scale nitrate distribution or the large-scale phosphate distribution, in fact, you don't simulate huge differences with a quota model. So, but if you're interested in, again, in the seasonal cycle, in specific areas like in oligotrophic areas, or etc., then it could be you have to use a quota model. But for the kind of questions I mentioned, no. It's not another world. So using a quota model does not bring you to another world.
Okay, thank you. Any other question? Yes?
At the end, let's say that in the regions with extremely high productivity, the model doesn't do as well. What did I miss here?
Okay, so I'm not sure, but you mean, does the model works better in a quota version relative to standard version in highly productive region?
Yes.
So, okay.
Yeah.
So you did the question, you get the question, Olivier?
Yes, my answer is no. No. In fact, no. There is no, it's not necessarily where a quota model will lead to a huge difference. So will lead to significant differences. Huge, I don't know, but to significant differences. So it's not in very productive. So I would say, in fact, in very stable environment, and when I say stable, so I mean stable over time scales of weeks, then a quota and a mono model, they will, basically, they will perform pretty much the same. And you can demonstrate that the fact that even mathematically, you can demonstrate that in stable environment, they should simulate pretty much the same thing. Not fully, but they will simulate the same thing. So it's really in variable environment. So it means in productive, yes, but not productive all the time. So it means in variable, as I said earlier, in systems, in productive systems, for instance, where you have strong pulses, and so biological activity is very, very variable on synoptic synoptic timescales. Yes, the quota model is performing better or should perform better in theory. But it's not a question of productive or not productive system. It's really a question of variable and or stable system.
Okay, thank you. Any other question? No? Okay. So, thank you very much, Olivier.
Thank you.
Yes.
Hope you enjoy the talk, and it was not too long or too difficult. And then Vincent will give a talk after me. No, am I right?
Yes, at 11:15, I guess.
And so you have a break.
Yes.
Okay,
So thank you very much. Can you send me your presentation so I can put it
in fact, I tried to
upload?
upload it on the Google Drive, etc. But it said that I have not the proper permission, the right permission to do it.
You send it to me and I will upload the.
I will send you a WeTransfer or something like this link.
Okay.
It's huge.
It's huge. Okay, thanks.
No
Okay.
problem.
Thank you very much.
So bye bye. Sorry, I have a meeting now, so I have to leave.
Okay. Thank you.
Bye. Enjoy your practical session, your training session. Sois fort.
Yes. Okay. Vincent, can you hear me?
Yes, I'm here.
Yeah. Okay. I think that we will have a round table on participants, I guess. And so we have a break at least for 35 minutes. And at 11:15, is it okay for you?
Perfect.
Yes.
Thank you for you.
Okay. Okay. Okay, thanks. Okay. Je sais pas. Vincent, can you hear me? Ah ouais, peut-être qu'il n'est pas là. c'est bon. Yes. Ah, yes. Yes. Est-ce que ça te va si on commence d'ici un quart d'heure, donc un peu plus tôt, en fait, la présentation?
Yes, no problem.
Ok.
Oui.
T'as
Combien de temps?
combien de temps à peu près, ouais?
Dans 10 minutes?
Non, mais t'en as la durée de ta présentation.
Ah, bah, ça peut. J'ai un gros morceau et un tout petit morceau.
Ok.
Donc, je peux faire soit le gros morceau et le petit morceau, soit que le gros morceau.
Les deux.
Bon, tu peux faire les deux. Ça peut,
On a le
ouais,
temps.
tu peux faire les deux. Ouais. Je pense qu'on a le temps parce qu'après, c'est la pause déjeuner. On fera pas de,
On fera pas de tes sessions
de-
TP ce matin.
on
donc,
fera pas de TP
voilà.
ce matin. Donc, non, non, c'est bien, c'est bien.
Ok, très bien.
Ok. Bah, on revient vers toi d'ici un quart d'heure.
Ça marche.
Ok. Là, même là.
Hello.
Hello, everyone. So I know, Vincent, it's just a sound check, okay? Because we will.
So
I'm not sure.
maybe
Your mic
Okay.
is working.
Yes, it's supposed to be.
So your
working.
audio.
there's a mouse settings, why don't you- So for the speaker, if you go,
So if you can just check on your speaker for the.
Okay.
let's see,
I see.
you've got many more settings than I do.
So I don't know why. Maybe. Okay. Hello, everyone. Blah 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 blah. No. I've got the GBL. So I need here to check the output. You agree with that? Okay. Hypnotic assist maybe. Hello, everyone. So nobody can hear me in the room.
Hello?
Yes, we are hearing you.
I'm not being heard because
Okay,
this.
let me check another thing.
Hello,
Maybe there's
testing,
some stuff
hello.
there. GBL.
Hello, hello.
Okay, so the output is the headset output. Nothing else to do. So it's in your Zoom interface.
Try playing the audio clip or a YouTube.
Hello, hello.
You click?
A YouTube clip and audio clip.
Okay.
File video. Then we can rule out.
So YouTube. Okay, this is all the stuff that my kids are watching.
Yeah, no.
You blame your kids. It's okay.
Okay, so Beatles. Sounds.
Oui, effectivement, j'étais écrit là, j'étais appelé à la téléphone. En fait, j'avais mon petit là qui il se plaint de fatigue et autres. Voilà. Donc, je faisais pas
Just the sound settings. Okay. Okay, so the sound is working.
Sound is working.
I guess that's
Maybe my output was too low, in fact.
I can. Can you use this computer?
No, I will use mine. I'm more comfortable. Is the microphone? No, so I think it's muted. Okay. Okay. So. This is your list of what I need to.
Yeah.
So, was a message there. I can hear you, please. Not sure what it means.
Sounds like they can hear you.
Yeah,
Yes.
they can obviously hear you because the mic is working. It's
Yes.
You on the side that needs to get the output. So it could be the speaker settings. So we need to figure out. So the mic is fine.
The mic is fine, okay?
The
So-
sound is fine. It's just getting it right on.
Maybe this
Yeah.
On Zoom.
Zoom.
This is the Zoom setting.
Trying to change that.
Okay. I don't see anything.
Did we test my Zoom? We didn't test my. It's working. Yes.
The speaker check here on the. Okay, it's work, but when I talk.
Yeah, maybe it's because. Could it be because? I wonder if when I talk. Hello.
Yeah, that's good. It's coming.
Okay.
So you spoke now, and I can do but
Vincent, are you there? Can you hear me?
Yes.
Okay. Great. So it seems to work. It's just for a sound check here because the PA, the public address, wasn't working, and now we have to do some checking.
Okay.
Okay. So.
Yes. So I guess for you, it doesn't matter. You just need to project your voice.
No, it's better if you don't want to have some feedback.
Yeah.
That's okay.
So if you need to go louder, I mean, it's just one thing.
I feel no.
Turn down the channel so that it's no slowly or the movie or with the so it's for bass, for treble.
Yeah, I think, we just, I think.
Thank you so much. I appreciate it.
Yeah. Okay. So if everybody's there, maybe we can start with the presentation, the lecture of Vincent, which is a French researcher at IRD. He's in l'Océan in Paris, and he has worked a lot on the with CROCO Advanced, more particularly in the Senegal and as well in Peru and Chile. So Vincent, can you hear us?
Yes, I can.
Okay.
I don't know if you can see my face. And I shared my screen, so can you see my screen?
No, not yet. No, we have an issue with the.
Does everyone have their screen up? Can you all see Vincent?
Yeah.
Can you all see Vincent? Yeah.
I don't know why.
I don't know what either.
I can stop sharing and share again.
No, it seems that there is an issue with whether
Okay.
my computer. I don't know why. Okay.
Yes.
Okay. You can start. Thank
Okay.
you.
So hello everyone. Thank you Renaud for the introduction. So I work at l'Océan with Renaud and Christian. And thank you for inviting me to do this presentation. So I will present some examples of biogeochemical studies with CROCO Pisces or ROMS Pisces, which I have done with many colleagues in the past. So I will show first three examples from the Peru upwelling system. It's a region I have studied a lot with Peruvian colleagues and French colleagues. So the first example will be on the long-term trends in the oxygen minimum zone. So this talk will be a lot about oxygen because it's an important variable in the ecosystem. The second talk will be on the impacts of climate change in Peru under the worst case scenario, RCP 8.5. And I will show briefly an example of what we did about submesoscale dynamics and their impact on the ecosystem in Peru. And if I have time, I will talk very briefly about what we are currently doing with Senegal. Okay, so first, just some basics about the CROCO model configurations that we use in the upwelling system. So we use CROCO Pisces, and CROCO, as you all know, needs open boundary conditions. So we use various types of models for the physics. Generally, they are global models of various resolution. It can be 1/12 of a degree, so it's approximately 10 kilometers. It can be 1/4 of a degree, 25 kilometers, or it can be like coarse grid models, like 2 degree, like what Olivier is currently doing, ORCA2 models coupled with Pisces. For the biogeochemical boundary conditions, we use sometimes output from models, but most of the time we use climatologies because when the models, the physical models, do not run with biogeochemical models, we need to use independent data. So we use climatology. They can be from the World Ocean Atlas, WOA, from CARS, which is a higher resolution climatology for the Atlantic and the Pacific. GLODAP, which is a climatology for the carbonates. And for iron, there is no climatology based on observation, so we have to use a simulation, a global simulation, which is ORCA Pisces. So using these boundary conditions, we force our regional model, and you can see here, so this is the coast of Peru in black, and we use this model to study the coastal dynamics and the ecosystem response. So I want to insist on the first steps, which is really a general aspect when you use CROCO Pisces or any kind of biogeochemical model coupled with a physical model. It's very, very important to evaluate the physics. So you need to use all the data that you can to make sure that your physical model is as realistic as possible. So if you have sea level, temperature, current, mixed layer depth, this is very important because of errors in the physics have a strong impact on the biogeochemical fields, and they can trigger a lot of errors. And you can have a wrong interpretation of your model output. So an example here for the Peru coast. The Peru coast is located next to the equator, so it is very impacted by coastal trapped waves that propagate along the equator and then along the coast. And so it's very interesting to use sea level height from satellite. So here in red, you have the Aviso sea level height, which is a collection of various satellites. And in black, you have the coastal sea level from ROMS in that case. And it's the data has been averaged in a box, the blue box that you can see on the left. And you can see a fairly good correspondence at various time scales between the two. So it tells you that in terms of sea level, the model is doing a relatively good job. If you have data, and this data is more difficult to get because it's in situ data, here we use some ADCP data collected over a number of years, 2008, 2012. And Alexis Chagnot, colleague of mine, did a climatology for this data to obtain the along-shore poleward current in the region. And on the right side, you have the ROMS, the mean along-shore poleward current. And you can see that the model is able to represent rather correctly the along-shore circulation. Okay, now we're moving to the biogeochemistry. So it's very valuable to use observation from space, like CWIPS or MODIS. So in that case, this is MODIS. So on the left, you have a MODIS mean chlorophyll in the Peru region, and you can see the high chlorophyll along the coast. It's decreasing offshore, so you have a very strong gradient. This is due to the upwelling of nutrients near the coast, which triggers a high biogeochemical activity. And on the right side, you have the model output for chlorophyll, total chlorophyll from Pisces. And you can see that it is able to represent the same structure, but you can also see some biases, like a too strong chlorophyll near the coast, and maybe some shifts of the cross-shore gradients as well. So the idea here is in all the studies, most of the studies that I did are process studies. So we are trying to get the closest model chlorophyll as possible to the data, but if there are some biases, we are not spending years to tune the model. I think you will have a practical course on how to tune the model this afternoon. But when you have very big models, it's kind of difficult. So when you are relatively happy with your model, you begin to do your process study. So in the next slides, we work with a model that has some obvious biases, like, for instance, a too strong chlorophyll near the surface. And then now, if you look at these small figures here, it shows the seasonal cycle of the chlorophyll, which is averaged in the coastal box in black. And you can see that the model is able to reproduce rather correctly the seasonal cycle in the box. But of course, since the chlorophyll is too high in the model, we have a shift, and we have some biases in the amplitude of the seasonal cycle. Okay, another interesting type of data to use when you want to validate your model is glider data. So this is something that we did off northern Peru during the El Nino event of November-December 2015. So on the left side, you can see the section that was repeated several times by the glider. So from point A near the coast to point B offshore, and the glider went 4 times from point A to 4B and back and forth. And so if you spread in time the sections of temperature that were measured, this is what you obtain in the middle from A to B, etc. And you can see, so in time, in the appearance of warmer water near the surface, which are due to the advection of warm water, which is typical of El Nino conditions in the region. And the model is roughly able, so in that case, it was a 4-kilometer model resolution. The model was able to represent rather correctly this warming. Then the glider had also some oxygen sensors, and so we were able to measure the oxygen. And what you can see is that there is the black ellipses show like a deepening of the oxycline, which is associated with the deepening of the thermocline as well, and warmer waters getting deeper. And the model is more or less able to represent this aspect, but the model, what you can see is that the model is representing correctly the orders of magnitude of the subsurface oxygen and of the surface oxygen. And so a characteristic of the Peru region is that the subsurface oxygen can be very low. It can be nearly zero. So you can have some anoxic events, which are also can be also found in Namibia, for instance, or in the Atlantic. Okay, so now we focus on 2 particular studies that we did with a Peruvian colleague, Dante Espinosa Moriberon. So the results that we present are based on 2 papers, one which is about El Nino, La Nina, and one which is about the long-term trends. So in that case, the configuration that we used was a 1/6 of a degree model. So it's not very high resolution for the time for this study, about 20 kilometers. But it was a long run, so 50 years run from 1956, 58 to 2008. And we used the SODA model for the physical boundary conditions and the CARS climatology for oxygen, nutrients, boundary conditions. And we also use the various atmospheric forcings for the wind and fluxes. I will come back to that. So the particular characteristics of the region is that there was a trend, a cooling trend observed in several fields. So on the left side, you can see a map of the trend of SST, AVHRR, SST trend. And you can see in blue and purple that you have a cooling along the Peruvian coast and also part of the Chilean coast. So this cooling is associated in the red square. There were in situ measurements of chlorophyll performed by the Peruvian colleagues. And you can see that there is also a chlorophyll trend, positive trend. So surface chlorophyll was increasing. Other observations of oxygen were also collected over a long period from 1965 to the late 2000s. And in the second part of the period, from 1980 more or less to 2005, you can see that the oxycline, which is the surface that separates the high oxygenated surface waters and the low oxygenated waters, so the oxycline is shoaling, so it's getting less and less deep in the recent decades. So the question, the observation is that we have kind of a consistent trend in SST, oxycline, and chlorophyll. Why is it consistent? Because we may think that there is an increase of upwelling, so there is colder water brought to the surface, along with nutrients which trigger an increase of chlorophyll, and also deep water which have a very low oxygen content are upwelled to the surface. So this is all consistent. And the question was, what is the forcing of this trend? Is it a wind forcing or is it something else? So first, the first task is to evaluate your model, your biogeochemical model with observations. So here we define the oxycline as the 20 micromole isosurface, which is shown here on the left side. And what we did is compare this oxycline depth. So the colors on the three panels indicate a depth from different sources of data. So you have the observations from IMARPE. IMARPE is a center, Peruvian center for research at sea. And they have collected a lot of observations over the years. And so the dots that you can see is the depth of the oxycline, which has been collected from different profiles near the coast. In the middle, you have the CARS climatology. So you can see that CARS climatology is somehow overestimated slightly the depth near the coast. There is less purple than in the IMARPE observations. And there is the model on the right, where you can see also this shoaling of the oxycline near the coast in the mean state, and with this blue-purple color near the coast. So the model is doing a relatively good job in the mean state. And now we can also look, thanks to these observations, we can also look at the variability. So here what we did is to collect all these profiles from IMARPE and compute the oxycline depth and average it over a box, which is shown here in red. And so you obtain a time series over a long period from 1960 to 2008. So in blue, you have the data, and in black, you have the model. What we did with the model is subsample the model output exactly in the same way as the observation cruises. And so you can see, what you can see is that there is a great deal of variability, and the gray bars that you can see are indicating the El Niño periods during which there is a deepening of the oxycline. And you can see that we can see this signal relatively well in the observations, and you can see that the model is reproducing them also, maybe not to the same amplitude, but we have a proof that the model is reproducing part of the variability during El Niño, at least. Okay, so in this particular work, what we are looking at is the trend. So what we did is to take all the data in this box, this orange box here on the left side, and compute a profile and compute the trend for different depths. So in red, you have the trend from the observations at different levels with the error. And in black, you have the trend computed from the model output. What you can see is that all these trends are negative over all the range of depths, except maybe below 200 meters, meaning that you have a deoxygenation over this time period, which is relatively well reproduced by the model. If you look at it another way, so if you come back to the oxycline depth shown by these 3 time series, so in black you have the model, in red you have the observations, and in blue you have the model but subsampled in the same way as the observations. So what you can see is that the model is relatively representing correctly the trend. But what you can see also is that if we subsample the model, we tend to obtain a very stronger trend. So meaning that the model tends to have, if we take all the data points, we have a much weaker trend in the model than if we subsample it, which means that maybe in the observations, in fact, we have a too strong trend, which is around 8.1 meters per decade here. So the real trend could be less than this observed trend. So what did we do next? So we are trying to attribute the trend to different forcings. So we investigated 2 possible sources of variability, the equatorial current or the local wind stress. So what we did first is to modify the boundary conditions. So here on the left side, you can see in blue, the blue arrows, they indicate the different currents that transport oxygen towards the Peru system. The EUC is the equatorial undercurrent. The PSCC and the SSCC are the subsurface countercurrents. There are 2 of these jets that transport relatively more oxygenated water towards Peru. And so if we turn off, First, if we turn off the variability of the wind, so we use only a climatological wind over the time period, we can see by the evolution that we don't change very much the oxycline evolution. So we get almost the same trend. Well, but when we turn up the variability of the boundary forcing, so we keep seasonal climatological EUC and subsurface currents, we can see that using different wind forcing, we obtained different oxycline trends, but these trends are no longer consistent. They are very weak, and they are no longer consistent with the observations. So with this experiment, this kind of experiment, we can attribute the oxycline trend to the EUC and neighboring currents trends. So it's really driven by a signal that comes from the equator. Okay. So now I'm changing to another typical example. which is a study that we did to investigate the impact of climate change in the Peruvian polling system. So this is a paper that we published in 2020. So I think most of you are familiar with the figure that is shown here, which shows the evolution of the radiative forcing in semi-5 climate scenarios. So the different colors show the different types of scenarios. So in the study, what we did, we investigate the worst case scenario, which is the RCP 8.5 scenario, which is shown here in gray. And we studied the impact of this scenario on the Peruvian polling system biogeochemistry. So first, just to, if you've never heard of this type of study, it is well known now that the CMIP5 models, for instance, and most of CMIP6 models also have this kind of bias. They don't represent correctly the dynamics in the polling systems. So here, for instance, is the SST of the IPSL CM5, sorry. And you can see in the Peru region that it's not able to represent the polling signal. We have warm water near the coast. And on the right side, you can see that these are the observations from Pathfinder. And you can see that the model is not doing a good job. So the polling is really weak in Earth system models. Sorry, I didn't define this term. So these coupled models, climate models, which have biogeochemical models in them, coupled to them, are called Earth system models, ESM. So there is no or barely coastal upwelling in ESM, so it's necessary to use regional models to downscale the climate signals and the biogeochemical signals. So as I said, we used the RCP 8.5 scenario, and we chose 3 Earth system models that relatively had a relatively weak bias in biogeochemistry in the equatorial regions. So these 3 models are the CNRM CM5, the GFDL ESM2M, and the IPSL CM5A MR. And there we used a configuration at 10 kilometers for Rome species. So first, I'm going to give you some elements on the physical response, because it's going to be a very important driver of the biogeochemical response. So if we look at the wind stress in the coastal region, what you can see is that one of the models, the GFDL model, is presents a stabilized upwelling favorable wind stress. So there is barely no change, whereas the 2 other models, IPSL and CNRM, they show a decrease in the wind stress over 100 years. If we compute the vertical velocity in this coastal box to quantify the upwelling, we obtain expectedly almost no variation in the simulation which is driven by GFDL, but we obtain a strong decrease in CNRM and IPSL. So what you can see first is that there is a lot of variability in the regional model, as you can see in blue, which is not present in the wind stress. It comes from the boundaries. And what you can see also is that the strength of the decrease of the upwelling is twice as strong as the wind stress. So it's not linear response. If we now look at the SST from Rom's model in the 3 scenario, driven by the 3 different models, we have a range of variation. What is interesting to see is that all of them present a warming, and this warming can range between 2 and 4.5 degrees in the box. So 4.5 is going to be a huge change for the ecosystem. Now let's go to the biogeochemistry. So on this first figure, what you can see is the nitrocline depth in the ESM model. So this is without downscaling. And this is in the box, the coastal box close to the Peru coast. In green, what you have is the climatology from local data from the IMARPE, the Peruvian Institute data. And you can see that the nitrocline in this box, in this coastal box, is around 20 meters. So first, what you can see is that there is a large bias between the three models already in present state. If you look in 2010, you can see that there is more than 20 up to 80-meter depth change between the nitrocline, the observed nitrocline, and the model nitrocline in these SM models. What you also can see is that the trend, the evolution of the nitrocline in the SM models can be very different in the three models, but they all seem to decrease. Now, if we use ROM-SPISCAS to downscale these signals, first we can see that we are able to correct a large part of the bias. Now the bias is almost there is almost no bias at the beginning of the time series for the ROMS CNRM simulation, and there is still some kind of bias, but 10 to 15 meters for IPSL and GFDL. What is striking also is that you have very different, well, not that different, but you conserve some of the trends in the deepening of the nitrocline, but they have very different amplitudes. Now, if we look at surface chlorophyll in the global models and in the regional model, in the same region, on the left, what you can see is that also very different levels of chlorophyll, from 0.1 to 0.2 to 0.6 on average, whereas in the real world, you have around 3 to 4 milligrams per square meter per cubic meters in the system. So you can see that the global models are not able to represent the correct level of chlorophyll. When you use the ROM-SPISCAS model, you are able to retrieve a relatively correct mean signal. Here we can see that it's slightly biased positively, so we have slightly too much chlorophyll in the regional models, between 4 to 6 milligrams per cubic meter. And what is quite striking is that you have very quick changes. For instance, the black curve, which is from ROMS CNRM, shows almost no change and a strong variability. And the blue and red curves, they show almost no change, just a weak trend of around 10%. This is quite surprising, because if you look just above this figure, you can see that the black and the red, so CNRM and IPSL, show decreased nitrocline. So how can we explain that there is a very little impact on the surface chlorophyll? Well, if we look in more detail at the vertical structure, so here is the trend computed at different depths from a mean cross-shore section. So what you can see is the black lines indicate the mean chlorophyll. So you can see the mean chlorophyll is higher near the surface and close to the coast. And the color shading is the amplitude of the trend. And so you can see that two models, ROMS CNRM and ROMS IPSL, show an increase slight increase of the surface chlorophyll, but we can also see it, but it's really much weaker in RUMS GFDL. But what you can see is also that they show a consistent pattern at subsurface, which is a blue pattern, which means that subsurface chlorophyll is decreasing. So in fact, what happens in this system? We saw that there is less nutrient in subsurface layers, but there is also less upwelling, so less offshore transport. So this less offshore transport means that there is more phytoplankton that remains close to the coast. There is more retention near the coast. So there is kind of a concentration of chlorophyll near the coast, just due to the physics, because of these surface currents. There is also a shallower mixed layer. This is something that I didn't show, but that is represented in all the models. And so all these effects lead to a stable phytoplankton concentration at the surface and to a reduction below due to the lack of nutrients. So one conclusion that is important from this work is that if you look at the satellite chlorophyll evolution in time, you will see an increase. So this increase could be a reassuring message saying, okay, maybe we have no problem with this, with the upwelling system. They will be rich. They are rich now and they will be rich in the future. But these model experiments show that maybe at the surface, it's another story. Okay, so now I'm switching to the third study in the Peru system. So in this, this time it was with some German colleagues. We were interested in the impact of the small scale, very small scale dynamics in the Peru upwelling system. So we are looking at the sub-mesoscale. So this is smaller scales than the mesoscale. And to study it in the Peru region, we had to move to a 2.6 kilometer simulation in a particular region in the south of Peru. So with 2.6 kilometer resolution, you are able to represent part of the sub-mesoscale spectrum. Not everything, but part of it. And you can see in this picture that we represent in a finer way the filaments. So first, I want to come back to some basics in the upwelling system and show you that in fact there is a lot of subduction. On the sketch on the left side shows the shelf, the coast, and the coastal wind, and the black arrow shows the upwelling for the subsurface part and the Ekman transport towards offshore. So this is the classical view and maybe the naive view of what happens in an upwelling system. Because in fact, in upwelling systems, you have strong thermal fronts. So how can the water at a certain temperature, so relatively cold water near the coast, go through a thermal front like this? In fact, if we have strong fronts, you create a series of subduction and abduction on both sides of the front. So what will happen is that you will have subduction on the cold side of the front, and you have upwelling on the warm side of the front. So in upwelling system, you have a lot of subduction, meaning that a lot of nutrients that come to the surface are subducted by submesoscale features and filaments. So this is an example based on observations from a paper of Thompson et al. This is based on glider measurements. So on the left side, you can see the SST and the glider track in gray, which has been repeated several times in this region. Then the middle panel shows the oxygen. And what you can see is that there is a lot of oxygen near the surface in red color. And this oxygen tends to subdux below a less oxygenated water that is located offshore. And you can also see the subduction of chlorophyll occurring near the front, on the right side. So what we did with in this study is to use this model at 2.5 kilometers. First, we validated it. So we validated the physics and also as nicely as possible the biogeochemistry, because there was a cruise taking place at the same time. And then what we did is to try to follow the water masses using a Lagrangian approach. So what we use is the ROMS offline model. So I don't think you're going to have a course, or maybe you had one last year, I'm not sure, on ROMS offline, but it's a very useful tool to follow the water masses and their characteristics. So what we did is to put a lot of parcels. These are the black dots that you can see in the blue cold water in the figure. So each one of these dots is a Lagrangian float that we followed in time to look at subduction. So in the bottom panel, you can see the parcel trajectories and their evolution of temperature. So you can see that they are captured by eddies and filaments, and they can be adducted very far offshore in rather rapidly. And you can see that their temperature can change also very abruptly. And so on the right side, what we did is to separate the parcels that were subducted and the parcels that were not subducted. So the parcels that were subducted were the parcels that left the mixed layer a short time after being upwelled. And what we did is to look at the depth of the parcels first. So you can see that the parcels that are not subducted are in red. Sorry, I forgot to tell. So the dashed black line is the time where the parcels are considered to be upwelled. So you can see that their depth is around 40 meters, and they are considered upwelled at around 30 meters. And then they remain in the surface layer, so between roughly above 30 meters. And the red envelope is a spread of all the parcels' depth. Whereas in blue, what you can see is the subduction. So you can see that in blue, the particles also go towards a shallower depth. They are considered upwelled at time 0. And then what you can see is that their depth is going to increase again. So they are really subducted. Expectedly, if you look at the nitrate evolution of the group of parcels, if you looked at the parcels that are not subducted, so the nitrate is around 20 when it gets into the mixed layer, when it is upwelled, and then the nitrate is decreasing, which is represents that biology is taking up the nitrate. So there is primary production consuming the nitrate. Whereas when you look at the parcels that are subducted in blue, you can see that the nitrate evolution is very weak. So you have very little primary production taking place because these floats, these parcels, are too deep, and they are roughly nearly below the euphotic layer. Then this allows us to compute an amount of parcels that are upwelled and subducted. So we can count the floats and look that around 43% of the upwell floats were then subducted a few days after. And so it means that it represents that around 40% of the upwell nitrate was subducted without being consumed. So a huge part of the nitrate, that is, of the nutrients that are upwelled at the coast, are subducted again in these filaments, in these cold filaments that go rather deep. Okay, so that was my last example on the Peru system. And if I have a little more time, I think I do, I can talk to you about a recent study that we did in Senegal. So this is part of the PhD work of a young doctor, Abdul Wahab Tal, from Senegal. And we modeled the dissolved oxygen cycle on the Senegalese shelf. And we analyzed the processes, physical and biochemical processes that drive the oxygen cycle there. And we also did some Lagrangian analysis. So the context of this study is the deoxygenation trends that have been measured in many coastal areas. Here you can see in red, this is a figure from Brightburg showing the hypoxic areas, and in blue the offshore hypoxic areas. There is almost no data in Senegal, in contrast with the Peru region, where there is an institute that is taking data for many years. In Senegal, there is barely measurements of oxygen, very little. And this is a plot from a paper from German colleagues that have collected the data. And you can see that near Senegal, it's nearly white. There were a few data collected in the late 80s, early 90s that suggested that the low oxygen, some low oxygen concentrations that were encountered there could trigger mortality of some fish, Serinade fish. And also, really recently, in 2012, there was the first measurement of total anoxia over the Senegalese shelf during the upwelling season over the Senegalese shelf. Another element that motivated that study is that we put a colleague of l'Océan, Alban Lazare, started a project and put a buoy on the Senegalese shelf, where I collected physical data, but also we were able to put an oxygen sensor near the bottom, and this oxygen sensor managed to measure a rather long time series, which is shown here on the left side of bottom oxygen. So this motivated to study the bottom oxygen variability. Here in this presentation, we focus on the upwelling season. So we are trying to understand the role of the physical and biochemical processes controlling the dissolved oxygen budget. And also we studied the characteristics of the upwelled source waters using a Lagrangian approach. So I will show you that in the second part. So this is the model. I can skip that part. Just briefly, the model configuration. We use a model with a zoom, a 10-kilometer model which covers the West African, Northwest African part of Northwest Africa. So Senegal, Mauritania, and the south of Morocco. And we have a zoom at 2 kilometers in the Senegal region. And we have 50 levels in the vertical. The four things that we use are ASCAT wind stress. We use daily wind stress to be able to represent the variability of in the cooling season. But we use a climatological heat and surface heat and freshwater fluxes from COADs. For Pisces, we use the climatological dust deposition. And for boundary conditions, we use also daily variable physical conditions from Mercator. and for PSCAS, the World Ocean Atlas and CLODAP data. And with PSCAS, so we performed an oxygen budget, and we also looked at primary production, export, etc. So first, let's look at the validation of the model. So in purple, you have the observation that I just showed in the previous slide. So it's near the bottom. And in black, you have the time series of the model, which shows that the model is doing a relatively good job in the early 2015 period. Also in early 2016, the model does not reach as low oxygen as the observations. And also in 2018, on the right part, you can see that the model is able to present rather correctly part of the variability. There are strong intraseasonal fluctuations related to synoptic wind events. And what you can see is that of the observations also occasionally are below the hypoxic level of 60 micromoles. So overall, we were quite happy because we have a fairly good match between the model and the observations. And what we are going to focus in the next slide is the upwelling season, which is roughly the heart of the upwelling season is between February and April. So it's a 3-month upwelling season. Okay, so first, let's look at the bottom oxygen on the left side. So what you can see is that there is a relatively oxygenated water over the shelf for depths larger than 20 meters. And then you have a strong gradient of oxygen along the bottom between 20 and 50 meters. Then you have a very low oxygenated water, which corresponds to the oxygen minimum zone that is found offshore of Senegal. If we look at the equation that drives oxygen, we can separate it into biological sources and sinks in blue and dynamical sources and sinks in red. So what you can see in the middle panel is the sum of all the dynamical processes. And so it's a positive term that is bringing oxygen to the system. And we will see later how this works. And expectedly, for the bottom, we have a blue term. Everything is negative for the biological sources and sink. So on average, biogeochemistry is a sink of oxygen. So let's first detail the physical processes. What we can do is separate them into advection and vertical mixing. So in the first panel, you can see that advection is a negative term. So what is happening is that it is bringing less oxygenated water to the bottom layer from the deeper regions. So in black are sketched the bottom currents, and during upwelling you have these bottom currents that transport low oxygenated water from deeper layers towards the shelf. And you can see that this term is very strong where you have a strong gradient of oxygen. And this is compensated to a large extent by vertical mixing. Vertical mixing is mixing, so it's a period of upwelling, so there is a lot of wind and a lot of mixing. So it's mixing the surface oxygenated water with the subsurface low oxygenated water. So it's bringing oxygen to the subsurface layer. Now, if we look at the biogeochemical processes, we can separate the sources of oxygen from production. So because the shelf is relatively shallow, you can have photosynthesis up to the bottom in this region. And if we look at we can look at the two sources, two kinds of production. First, the regenerated production on the left side. You can see that it's taking place over all the shelf, and it's dominating over the new production. So new production is due to the upwelling of deep nutrients. So in this case, it's you have nitrate that is upwelled in the north here. And so it is then adducted towards the south and consumed. So new production takes place mostly in the north part of the shelf. And on the right side, you can see a figure from a previous paper by Ndoye et al., which is showing the vertical velocity in the region near the bottom. And you can see that you have a strong structure, very high values of bottom vertical velocity, showing that upwelling is occurring mainly in the north. So this is where nitrates are upwelled. Then if we look at the sinks, we have remineralization of organic matter, so production of organic matter in the surface layer. Then you have transport of organic matter with the currents towards the south, and this organic matter tends to sink over the shelf and is remineralized, and this remineralization is consuming oxygen. Then on the right side, you can see also that you have a lot of phytoplankton. Sorry, you have a lot of zooplankton, which is growing over the shelf, and due to this mixing, the zooplankton also is present in near the bottom, and it consumes oxygen just by respiration. So this was the analysis of the oxygen budget. So in the second part, we were also interested in studying the origin of the water parcels that get to the mooring. So what we did is to release floats at the mooring site, but now what we did is to transport floats backward in time. So what does it mean? It means that if we are able to looking at all the water parcels that converge towards the mooring. So the floats were transported backward in time for 30 days. We released 500 floats between 30 and 40 meters around the buoy, which is called Melax, every 5 days in the period 2015-2019. So it makes around 45,000 floats in total. And what we do is, along the trajectory of the floats, we store the dissolved oxygen concentration, the depth, but also the terms, the physical and biogeochemical terms that are responsible for the evolution of oxygen. So on the middle panel, what you can see in color is the depth of the particles. And you can see that you have also what has been plotted is the position of the particles between 30 days before they reach this red square and times 0. So you can see the trajectory, the main trajectory of the floats that converged in this region. So you have floats that come from the south, but you also have some floats that come from the north, and you have some floats that are relatively shallow in blue that comes from the shelf. On the right side, you can see the spaghetti of the float's depth in time. So, and in black, you have the mean depth of the floats, showing that the depth of the float tends to increase to reach the depth of the mooring, which is around 40 meters. So what we did is to look at the oxygen evolution along the pathway of the floats. So here, it's the we took all the flow together and computed the mean oxygen evolution. So in black, you have the climatology, which is the mean of all the trajectories. And in color, you have the trajectory for the different years. So what you can see is that there is an increase of oxygen over the months before they reach the mooring, increase for more than 30 micromoles. And you can see a relatively large variability between the different years. You can see also a weak change during the first 15 days and a strong change during the last 15 days where the floats are really close to the shell. So there is a strong internal variability, as I said, and if we look at one particular year, 2017, we can see that there was a much lower oxygen in 2017, and we were interested in knowing better why. So what we did is to investigate the different terms of the oxygen equation along the trajectories. So what is shown on the right side is for each year, you have some blue terms and some yellow terms. The blue terms correspond to the terms computed over the period 30 days to 15 days. And the yellow terms correspond to the period 15 days to time equals 0. And what is positive is bringing oxygen to the water mass during its course towards the mooring. And what is negative is subtracting oxygen to the water mass. So if you look at the year 2017, which was the most particular year, what you can see is that there was a relatively low contribution of oxygen by vertical mixing in 2017 and 2016. So there was less mixing. What you can see is that in 2015, there is a very strong vertical mixing in comparison. So this is the first contribution, is that less mixing brought less oxygen to the water mass. Also, what you can see is that there was a relatively low a relatively high consumption of oxygen during 2017. If you look at the yellow bar was relatively important, as important as 2018, but in 2018 the vertical mixing was compensating. So this low vertical mixing and high dissolved oxygen consumption in 2017 is the explanation of the low oxygen in 2017. What is also striking in this figure is the very strong mixing and very strong consumption in 2015, which in fact do not have a strong impact. If you look at the end in 2015, we are just slightly above the mean. And the reason for that is that this was a particular year with much shallower trajectories in this year. And when you have shallower trajectories, well, you have the particles where the water mass was closer to the surface. So we had more ventilation, more mixing, more effect of the wind. And also when we are closer to the surface, there is more dissolved organic matter to be remineralized. So the remineralization was stronger. So to conclude, we show that the physics brought dissolved oxygen and biology consumed dissolved oxygen in the bottom layer of the continental shelf during the upwelling season. Advection tended to decrease dissolved oxygen on the shelf by transporting the low dissolved oxygen subsurface water onto the shelf, while vertical mixing ventilates the bottom layer. Consumption by remineralization of organic matter was strongly compensated the production of dissolved oxygen by photosynthesis in the bottom layer. And when the conclusion from the Lagrangian part is that the source waters show very high internal variability with the lowest oxygen levels encountered in 2017 associated with reduced vertical mixing. So thank you. I have finished my presentation, and if you have some questions, I will be happy to answer.
Okay, thank you very much, Vincent. So if you have any question in the room or online, don't hesitate. Yes.
Can I ask about the oxygen budgets? Is it what time scales for vertical mixing subtraction units? Do you have to run an oxygen budgets online as well?
Okay. Have you heard the question, Vincent?
No, sorry, can you repeat it, please?
Yes, okay, I will repeat it. Is there any possibility to do some oxygen budget online with the model? I think that's the point. Yeah. Okay.
Yes, sorry. So I didn't, maybe it was not clear in the last presentation. So in the last presentation, there was an online budget. When I showed you the maps of the different terms, this was from an online budget of oxygen. So it is, in fact, it is possible to activate diagnostics for any tracer in PSCS. I won't get into the technical part, but there is a CPP key for that. Well, you cannot, of course, store all the terms for all the tracers in PSCS because there would be too many terms, but you can do it for a few tracers. So here we did it for oxygen. And so we have a term for vertical mixing, for advection, horizontal advection, meridional advection, zonal advection, and vertical advection. You have also a term for horizontal mixing, but generally it is negligible. And you have the rate, a term for the rate of oxygen evolution. So that's how we did the oxygen budget. So it was online. And then the second part is more something that is not very commonly used, is that we use the fields of the different terms, and with the Lagrangian, we were able to sample these fields, these 3D fields, along the trajectory of the flows. That's what he did, and that's why we have this offline term. I hope I'm clear.
And what about the frequency of this budget? Is the question?
The frequency. In this experiment, we did. You mean on the online budget?
Online.
Yes, on the online.
On the online budget, we did. In this time, we did a daily output, which is kind of heavy, but we, as I said, we did it only for. I think we did it only for temperature and for oxygen, not for the other tracer, maybe for nitrate, but I'm not sure. So it's possible to do it. If you want to put more tracers, probably you need to decrease the sampling to maybe a month or maybe 5 days to have not too big files. Maybe it depends also if you use XIOS or not. In our case, we did not use XIOS, so maybe with XIOS there is a way to have maybe not too big files or separate files. I don't know.
Okay, thank you. So, any other question? Yes, online. So, I cannot see the question. Okay, Frédéric.
Hi, everybody. Thank you, Vincent, for this presentation on biogeochemistry. Just a slide on which you are presenting the nitrate decline. You present the profile of ESM model, and you said that there are biases on ESM model. As we observe, the ESM model present the future projection until 2100. And I want to know on which base you declared, which is the reference from which you calculated these biases until for this future projection.
Okay, so maybe I was not clear enough. I'm going to show the slide again. Can you see?
Mm-hmm. I can
Yes.
see it.
Okay, I'm going to go back to this figure because I didn't want to send the wrong message. Okay, so here.
Yes.
I was talking about the bias. Can you see my mouse?
Yes, clear.
Yes, so I was mentioning the bias at the beginning of the time series. So we put this line. This is the data, okay? So we put a line just to show where the present level of nitrocline was. Of course, we don't think it's going to be unchanged, but it's just to compare this depth here, 20 meters, with the depth of the nitrocline in the ESM models, which is 60, 80, 90 meters. So there is a huge difference, and this is why I said there was a huge bias, in nitrocline depth in the ESM models.
So yes, so in the green we have observation data.
Yes.
So you have considered the interpolation until the end of century.
Yeah, that was just okay. Don't forget this line. Just
yes,
maybe we should have put just a big green dot here.
Yes.
In 20,000. Maybe it's
so the biases was calculated related to the data in 2010.
Yes, it's related to the data in 2010.
Maybe it's not. Maybe when we go to the future, this could not be based on the bias on the model. Maybe this can depend on other mechanisms of climate change, global warming, something like that. So we see clearly that as we are going far from the time, the bias, the difference become great. So I don't know if we can call it biases or this depend on another mechanism.
Yes, I agree. It's sorry, it was a bit misleading. So the bias is only for 2010.
Okay.
Forget about the rest of the
okay.
dash line.
Okay, thank you.
You're welcome.
Yes, another question that I can have to you is if is possible to force the CROCO model with ESM parameters to get home speed case result. What I mean is that if CROCO model can be used for feature projection to be forced with, for example, for RCP 4 and 5 or 8 and 5 model, and we can still call this CROCO model forced by ESM climate model.
Yes, of course. In this study, I want to point that this study was a lot of work because we did very long runs. It was the first time that we did 100 years with CROCO Pisces, so it took a lot of time, and we did it for 3 models, and also there were some bugs, so we had to redo some simulations. So it was a lot of work. So we focused only on the worst case scenario, which is the RCP 8.5. But of course, the same approach could be repeated for the other scenarios. And
okay.
For SEMI 6, probably.
Sorry for a last question, if you allow me.
Yes, yes, yes.
Okay. Yes, you are doing a great job in Senegal and Peru. So I don't know if we can shift to the Gulf of Guinea zone, looking for other parameters of biogeochemistry, probably simulated in your model, like total alkalinity, inorganic carbon, pH for ocean acidification or carbon floss variability. Thank you.
Yes. Okay, so I'm not an expert on that, but of course it can be studied with Pisces. I didn't show all the work that has been done with CROCO Pisces. I have a colleague in Peru who has done 2 papers on the carbonate system and pH, and yes, it can be done with Pisces. It can be done in other region.
Okay. Thank you. Thank you.
Okay, thank you. Yes, you have a question from Jennifer. Yes, come here.
Hi, Vincent. I
Hi.
hope you can hear me. It's
Yes.
Jennifer from Sound. Thank you so much for that. I really enjoyed it. So I was interested in your bottom dissolved oxygen experiment, that the last bit that you presented. How important is it to couple a sediment model? And if so, is it better to have a two-way nesting, or is it sufficient to be, just one way?
Okay, so that's an interesting question. So maybe you know that Pisces has a new sediment model. So I don't know if you're going to see that in the course, but I guess in the future it will be possible to couple CROCO Pisces with the sediment model. So in this study, we didn't use the sediment model because it was not available, and so the sediment is represented in a very, very simplified way. And in fact, we were quite well surprised to see that the model without the sediment model was able to represent rather correctly the oxygen cycle very near the bottom. Well, our data is not completely at the bottom. It's a few meters above the bottom. So maybe very near the bottom, we would have some surprise, and not maybe the model is not really correct. But what can I tell you more is that there is a colleague of mine that's going to work on this sediment model and to implement it in Senegal. So in a few years, I guess we will know if we did a good job, or how it can be improved with the sediment model. Then you mentioned the two-way coupling. So did you mean two-way coupling with the sediment model, or two-way coupling with the big grid and small grid?
I was thinking about the two-way nesting with sediment coupling, or is that not something that is ready or on the table yet?
Yes, so it will be a two-way sediment coupling, of course. I think, well, you can talk about it and ask Renaud about it as well, because what we saw is that this sediment model needs a lot of time to be integrated, to be at equilibrium. So in fact, Olivier could talk much better than I about the subject, but it needs hundreds of years of runs just to reach equilibrium. So what we need before being able to couple it properly with CROCO Pisces in the water column is to have a tool to reach faster the equilibrium state. So I think there's going to be some work in the future years to be able to have initial conditions for the sediment model without doing the coupling with CROCO Pisces, because it's not possible to run it for thousands of years, of course. And so then it will be a two-way nesting, because yes, unless you only are interested in the sediment, you need a two-way nesting to be able to see how oxygen is consumed and if nitrate is released from the sediment, depending on the conditions, etc. So yes, it would be two-way nesting.
Okay, thanks very much.
You're welcome.
Okay, any other question? Yes, Precious.
So I saw that there is a lot of respiration at depth.
Maybe you can come here.
So from your presentation, I saw that at the last slide that there's a lot of respiration at depth. So the question is that I don't know if you've looked at the carbon. Does that mean that the biology doesn't all the carbon that is taken up in the surface is respired completely? That our biology doesn't draw down carbon in that region, or is it transported in a different direction towards the deep ocean? Or you have organic matter forming, and then at depth, everything respire that you don't have biology playing a role in taking up carbon in that region. I don't know if it's something you have looked at. Is that?
What we did is I didn't show it in the presentation, but actually there are two different seasons. So you have the pooling season where there is a formation of organic matter, and then it is transported to the south, and also there's a lot of variability. So I think that part of the carbon is transported offshore, but in the warm season, it's much more like a 1D system. So all the carbon that is formed it remains in the bottom layer, and there is a lot of remineralization, and it can lower the oxygen further than during the pooling system. In fact, during the pooling season, at some point. Besides that, I hope it answers partly your question.
Yeah, no, that sounds good. It depends on the time of the year.
Yes.
Thank you.
Okay, thank you. Other question? No? Okay. So I think we're done. Thank you very much, Vincent.
Thank you, and have a nice practical session with the guys.
Yes.
Okay.
Can you send me your presentation so
Yes.
that I can put upload it on the?
Yes,
on the
I will send you a link.
Okay, thank you very much. Okay. Bye-bye.
Bye-bye, everyone.
To share the interest.
Yes.
Maybe they can put their video on.
Yes. Maybe for those who are online, maybe you can present us your motivations and the interest you have in the specific field who would be explored this week. So maybe we have Hector, Aziz, Chicana, I guess, Laura as well. No, is here. Okay, sorry. Leonard. So, and Frederic, of course. Ah, you are Leonard. Okay. So maybe Frederic, would you mind to present your the topic of interest here?
Are you talking to me, please?
Yes, we are.
Okay. I was yes. Yes. Now I'm listening to you.
Okay. The idea was to present a little bit your topics and the interest you have in the different fields that will be awarded this week. So in sediment or biochemistry or earth interactions.
Yes. This will be when the presentation. When do you want me to present?
No, just a brief presentation.
It like a presentation or just discussion?
No, just if you could introduce yourself briefly now, and what your interest is in particularly.
Yes. Okay.
Just briefly.
Yes. Now or after now?
Right now.
Okay, thank you. Yes, my name is Frederic Bonu. I'm researcher lecturer from Benin. Yes, I work with yeah, I'm physical oceanographer. I'm interested in CROCO model, not only CROCO model, general model. So we work also with model data, mainly ESM climate model. And one of our projects on which we are working now is climate geoengineering model. We use semi-per models, like yeah, the model that Vincent present, like RCP model. Yes, the variable that we work on, we have worked on for the climate impact was precipitation, salinity, temperature, and also ocean circulation. And now we will have a next round of the project probably in next year, and we work mainly on sea level rise and also biogeochemistry, mainly zooplankton, phytoplankton, nitrate, oxygen, in general, the nutrients. Yes, at the beginning of this year, I attend a meeting, a CROCO workshop or CROCO training as like this workshop with a Chilean guy, mainly the guy who present Andres, who present CROCO Live. We was with them in January. I have started discussion with him of a potential collaboration, and the variable of the variable that I want to model in West Africa, mainly in north of the Gulf of Guinea, will be yes, the physics, ocean circulation, the biogeochemistry, mainly alkalinity, total inorganic carbon, CO2 flows, chlorophyll, zooplankton, and so on. And also, I'm interested, I said, in the part of, I think this is Benchila or Rashid, some if I don't forget the name. He has presented not during this workshop, but during the workshop, the training of January, the sediment transport, the hydromorphodynamics. So this is my interest. So, and I'm still in conversation with Andres from Chile. But if there is somebody in maybe in sort of Africa, recently I noticed that one of our students, because we have a regional program here in Master in Oceanography, one of our students did his master internship with Serena and Sandrine from Côte d'Ivoire. So, and I realized that there are people, or there are researchers also that already started working on CROCO model in tropical Atlantic Ocean. So, me, I'm interested not only for Gulf of Guinea, but also the tropical Atlantic. I think this should be nice if we can find a way to work in collaboration and activate these different parameters. As I asked the question to Vincent, he said that he's not a specialist of carbon, but there is a guy from Peru. I think we can start to do a kind of study with CROCO model here. So that is all.
Thank you very much. So
you're welcome.
Chikana?
Yes.
Yes, Chikana, can you present you? Can you hear?
Yeah, yes.
Are you asking me a question because I didn't listen to your last.
Okay, can you?
The question is for me or for?
Yes, it's for you. Can you introduce yourself?
Thank you.
Frederic, I thought. Sorry, no, it's for Chikana. It's not for you, Frederic.
Okay, thanks.
Okay. Good afternoon, colleagues. My name is Tikana. I work for the National Department of Forestry, Fisheries, and the Environment. My interest with CROCO is that I'm looking at various connecting patterns of HOE as well as sardines from the Western Agalas bank as well as the West Coast. So I'm going to be using the CROCO model output as the high resolution to look at those connecting patterns in my study, as well as looking at how the sub-mesoscale dynamics affect the recruitment variability. And thank you so much for this training, and I look forward to learning more as we go into the week. Thank you.
Okay, thank you very much. Hector, can you introduce yourself, please? Maybe Hector, can you hear us? Ah, okay. Okay, sorry. And Aziz, can you introduce yourself, please? Okay. So,
It's just Leonard.
Leonard? Yes. Who is Leonard? Okay. Then we have Leonard. Maybe you can introduce yourself. Okay.
I can
Maybe
introduce
later.
myself. Can I introduce
course.
myself? I can introduce myself. So I'm Jennifer. If you don't know me, I'm from SEON. Part of my job is orchestrating South Africa's operational forecast models, which is quite a scary place for me to go. But I have some other smart people helping me, and my heart still always belongs to ROMSO and ocean dynamics, particularly the Benguela and where the Agalis meets the Benguela. So for me, this advanced week is just a godsend because I'm learning as much as all of you guys. So anyway, thank you to you guys back there and you for your time. And that's me. We got no more people who want to introduce themselves.
No.
No. Okay.
Okay.
Do you want to call it lunch now?
Yes, maybe. Decide for lunch. We'll go back here in 1 hour to begin the hands-on session. Okay. Okay.
So I
No, it's okay. It's okay. It's okay. Okay, so if you are ready, this afternoon we will do the first hands-on session. It's a relatively easy session. It's quite easy, so it's straightforward. So what we will do, you will install and get the code, install the code CROCO Pisces, okay? We set the Benguela low resolution configuration, and then you will create with the CROCO tools the initial and boundary conditions for Pisces, okay? Then you will run the model just for 1 month. It's a short short run, and you will explore the results, physical and biogeochemical results you get. Okay, so that's it. The tutorial is in the Google Drive. You can access, I think that Jenny. Yes. Okay. And that's it.
Just to add something, to explore the result, we will use a new tools named Ferrets, not MATLAB.
Yes, so we have prepared all the scripts. Okay, so you just have to launch the script in Ferret. Okay, but if you want to use your own visualization tool, there is, of course, you are not obliged to use Ferret. Okay. Ferret. Yes. F-E-R-R-E-T. I think it's like yeah.
Is there a reason why you prefer Ferret?
Because it's quite easy to launch and do a simple plot with just one command. You know, you load the file, pop, you say a shade, you choose your time step, the level, and then plot, and you get the plot straight. It's really straightforward. Of course, if you want to have nice plot and nice analysis, maybe it's not the best tool, but
just for a quick look.
yes, exactly.
I can
You
send
have a
it.
question?
I did send it in the email. Does anyone read their emails? It was on Friday. Everything you need to know about CROCO Advanced. You see, I can send it again.
No, it's just Monday and Tuesday. There's no.
Shoot something. Try to reload, maybe. Zach, are you getting joy? Do you have something there?
I'm gonna check now.
I see it. I see it. It
It's
should be
all-
there.
Yeah.
Oh,
Yeah, yeah. I had
Je vois zéro différence.
Yeah, the option is down
Is it you? That's so weird. We had it with your neck last week. And she was sitting in that I've got them all here, don't worry.
Are you good? Yeah.
But you know the 32. These guys pass here. Okay.